January 5th, 1943. 1100 hours. The waters off Guadalcanal shimmer under a tropical sun that's turned the bridge of the USS Helena into a steel oven. Seaman First Class Thomas Reardon stands at his post in the aft 5-inch battery, hands resting on the loading mechanism of a Mark 12 gun that's already hot from the morning's patrol. The cruiser's been at general quarters for 72 minutes, and Reardon's sweat has soaked through his dungarees despite the wind screaming across the deck at 20 knots. Then the call crackles through his headset. Bandits inbound. 4 o'clock high. Reardon's gun captain, Lieutenant Red Cochran, doesn't need to check his radar screen. The sky to starboard suddenly sprouts 4 dark silhouettes, Aichi D3, a dive bombers, Vals, dropping out of a cloud bank at 8,000 feet and accelerating into their attack runs. The Helena's anti-aircraft battery erupts. 40mm Bofors pump streams of tracers skyward. 20mm Oerlikon's hammer at 450 rounds per minute. The 5-inch gun next to Reardon's position fires first, its shell screaming upward with a muzzle velocity of 2,800 feet per second. Through the chaos of explosions and smoke, Reardon watches something impossible. The first Val, still 300 yards from the ship, suddenly disintegrates. Not from a direct hit. The shell exploded near it, 50 feet away, and the aircraft simply came apart in the air, torn to shreds by a cloud of steel fragments that shouldn't have been there. Because that shell missed. It never touched the target. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Lieutenant Cochran fires again. 2 more shells. The second Val. This one diving at a 70-degree angle with its bomb clearly visible beneath the fuselage, meets the same fate. The shell detonates 40 yards in front of the aircraft's nose. The bomber flies directly into the expanding sphere of shrapnel and fire. Its engine tears free from the airframe. The pilot never has time to pull up. The wreckage hits the water 800 yards off Helena's starboard beam, sending up a geyser of white spray that catches the sunlight. 4 Japanese aircraft attacked the task force that morning. 2 made it back to their base. The other 2 were destroyed by shells that technically missed them. The gun crews didn't understand what they'd just witnessed. Neither did the Japanese pilots who survived, because the shells that killed their wingmen carried something inside them that had never been fired in combat before, a device so revolutionary that its development had been classified at the same level as the Manhattan Project, a technology that would fundamentally alter not just this battle, but the entire trajectory of the Pacific War. The United States Navy called it the Mark 32 VT fuse. The British called it the proximity fuse, sailors throughout the fleet called it the funny fuse, and Japanese air crews would soon learn to call it death. To understand why this moment mattered, you have to understand the problem that naval gunners faced in January 1943. The problem wasn't courage. American anti-aircraft crews stood at their posts during kamikaze attacks when rational self-preservation screamed at them to abandon ship. The problem wasn't training. Gunners spent weeks at shore facilities learning to track fast-moving targets, to lead their shots, to maintain fire discipline under stress. The problem was mathematics, specifically the mathematics of trying to hit a moving target in 3-dimensional space when both you and the target are traveling at high speed and the target is actively trying not to be hit. Consider what an anti-aircraft gunner on a cruiser actually had to do. The ship itself is moving. Perhaps 20 knots, roughly, 23 miles per hour, but not in a straight line. The helmsman is executing evasive maneuvers, turning, accelerating, decelerating, because standing still in combat is suicide. The gun itself is mounted on a platform that's rolling with the ship's motion in the swells. Even in calm seas, a cruiser might roll 5 degrees port or starboard. In rough weather, that could double. The target is an aircraft traveling at 300 miles per hour or more. Late-war Japanese fighters like the Mitsubishi A6M0 could exceed 350 miles per hour in level flight. Dive bombers attacked at even higher speeds, gravity adding velocity as they plummeted toward their target. And these aircraft weren't flying in predictable straight lines. They jinked, rolled, climbed, dove, anything to spoil the gunner's solution. The shell itself, once fired, became a ballistic projectile. It left the barrel at tremendous velocity, but it didn't travel in a straight line. Gravity pulled it down. Air resistance slowed it. Wind pushed it sideways. At 5,000 feet of altitude, a typical engagement range, a 5-inch shell needed roughly 3 seconds to reach its target. 3 seconds doesn't sound like much. But in 3 seconds, a Zero travelling at 350 miles per hour covered 1,540 feet, 4 city blocks. The gunner had to aim not at where the aircraft was, but at where it would be 3 seconds later, accounting for his own ship's motion, the target's motion, gravity, wind, and the projectile's ballistic arc. And then, even if he got all of that exactly right, the shell still had to actually hit the target. A 5-inch shell is 5 inches in diameter, roughly the size of a coffee can. A Zero fighter has a wingspan of 39 feet, hitting a 39-foot wide target with a 5-inch projectile at a range of 1 mile, while both objects are moving at hundreds of miles per hour in different directions, requires precision that borders on the supernatural. The Navy knew this. They'd been studying the problem since the 1920s, when it became clear that aircraft were going to be a major threat to surface vessels. Pre-war anti-aircraft doctrine relied on 2 types of fuses: contact fuses, which detonated when the shell physically struck something, and time fuses, which were set to explode after a specific number of seconds of flight. Contact fuses were theoretically ideal. If you hit the target, the shell exploded, and the target was destroyed. The problem was hitting the target. Analysis of anti-aircraft fire from the Pacific Theater in 1942 showed that gunners achieved direct hits less than 0.5% of the time, 1 hit for every 200 shells fired, sometimes worse. Time fuses were more practical. The gun captain would estimate the target's altitude and speed, calculate how long the shell would take to reach the intercept point, and set a mechanical timer inside the fuse before loading. If the calculations were perfect and the target didn't change course, the shell would explode near the aircraft, hopefully close enough that the shrapnel would cause damage. Emphasis on hopefully, and perfect, and didn't change course. The lethal radius of a 5-inch high-explosive shell using a time fuse was approximately 20 feet. Any further than that, and the shrapnel dispersed too much to guarantee a kill, might damage the aircraft, might wound the pilot, might do nothing at all. To reliably destroy a target, the shell needed to explode within 20 feet of it, but setting a time fuse required the gun captain to make his calculations before the shell was loaded. Once it left the barrel, that timer was ticking down to detonation regardless of what the target did. If the pilot saw the first burst and turned, climbed, or dove to evade, every subsequent shell with its time fuse already set would explode in empty air while the aircraft escaped. The statistics were damning. In early 1942, before the Helena's action off Guadalcanal, the Navy estimated it took an average of 2,500 rounds of 5-inch ammunition to down a single enemy aircraft using time fuses. 2,500 shells. Each shell weighed 54 pounds. A single gun could carry perhaps 600 rounds in its ready magazines. Do the math. One cruiser, firing all of its anti-aircraft ammunition at maximum rate, might destroy 1, maybe 2 aircraft before running dry. And Japanese doctrine for attacking American naval formations called for coordinated strikes by dozens of aircraft simultaneously. The losses mounted accordingly. At the Battle of the Santa Cruz Islands in October 1942, Japanese aircraft severely damaged the carrier USS Enterprise and sank the carrier USS Hornet, despite intense anti-aircraft fire from the entire task force. The ships fired thousands of shells. The official action report noted that most bursts occurred too far from the attacking aircraft to inflict meaningful damage. Gun captains, working under immense stress with incomplete information, were setting their time fuses either too long or too short. The shells exploded above the targets, below them, ahead of them, behind them, anywhere except where they needed to be. One destroyer captain, whose ship had expended its entire 5-inch ammunition load during a 45-minute attack without claiming a single confirmed kill, wrote in his after-action report, "Current anti-aircraft methods are inadequate against determined enemy attack, Without improvement in fire effectiveness, fleet losses to enemy aviation will become unsustainable. He was right, and the Navy knew it. Which is why they'd been frantically working on a solution since 1940. The concept wasn't new. Engineers and scientists had been proposing proximity-activated fuses since World War I. The idea was elegantly simple. Instead of relying on a direct hit or a preset timer, create a fuse that could sense when it was near a target and detonate automatically at the optimum distance. Turn that 20-foot lethal radius into a 300-foot acquisition zone. Make near misses count. The problem was execution. How do you build a device small enough to fit inside a 5-inch shell that can detect an aircraft? How do you make it rugged enough to survive being fired from a gun? The forces involved in launching a shell are catastrophic. The acceleration when the powder charge ignites subjects everything inside the shell to 20,000 times the force of gravity. 20,000 Gs. Instantly. Any electronic component, any moving part, any delicate mechanism gets crushed or shattered, and if it somehow survives the launch, it then has to function while spinning at 25,000 revolutions per minute as the shell spirals through the air, corkscrewing toward its target. The British tried first. Researchers at the Telecommunications Research Establishment worked on designs using photoelectric cells to detect the shadow of an aircraft passing overhead. The concept showed promise in laboratory testing. In practical field trials, it failed catastrophically. The photoelectric cells couldn't distinguish between aircraft and clouds. They triggered on seabirds. They malfunctioned in bright sunlight. And they were so fragile that the firing shock destroyed most of them before the shell even left the barrel. The Americans took a different approach. In August 1940, Vannevar Bush, director of the National Defense Research Committee, convened a meeting of the nation's top physicists and engineers. The question on the table: can we build a practical proximity fuse for anti-aircraft shells? If so, how quickly? The man Bush chose to lead the effort was Dr. Merle Tuve, a 40-year-old geophysicist who'd been working at the Carnegie Institution's Department of Terrestrial Magnetism. Tuve was an unlikely choice for a weapons development project. His expertise was in cosmic rays and ionospheric research. He'd never designed a fuse, he'd never worked on artillery, but he had one critical qualification. He understood radio. Tuve's insight was to abandon optical sensing entirely. Instead of trying to see the target, he proposed building a miniature radar transmitter inside the shell. The fuse would broadcast a radio signal. When that signal bounced back from a nearby aircraft, the fuse would detect the return echo, calculate that an object was within lethal range, and trigger the detonation. Radar itself was still cutting-edge technology in 1940. The British had been using primitive radar systems for air defence since 1938, but those were massive installations with antennas the size of buildings and power requirements measured in kilowatts. Tube was proposing to miniaturize that technology down to a package the size of a soda can, make it survive forces that would tear apart most mechanical devices, and power it with a battery small enough to fit alongside the explosive charge. His colleagues thought he was insane. The consensus among engineers was that the technical challenges were insurmountable. Vacuum tubes, the only electronic components available in 1940 that could amplify and process radio signals, were fragile glass bulbs filled with delicate wire filaments. They shattered if you dropped them. The idea that you could fire one from a gun at 20,000 Gs and have it still work seemed like fantasy. Tuve disagreed, and because Bush trusted him, Tuve got funding, laboratory space, and a small team of physicists to prove the concept. They called it Section T. The T stood for Tuve. By December 1940, Section T had moved from Carnegie Institution to a hastily constructed wooden building in Maryland and had grown to 15 scientists working 80-hour weeks. Their first challenge: develop a vacuum tube that could survive the shock of firing. The commercial vacuum tubes of the era couldn't do it. Tuve's team tested dozens. Every single one shattered during simulated launch conditions. They needed something entirely new. The engineers at Sylvania Electric Products in Massachusetts solved it. They redesigned the tube from scratch, using thicker glass, shorter wire filaments, and internal dampening structures to absorb shock. The result was the VT-158 tube, barely larger than a man's thumb, that could withstand forces no vacuum tube had ever been subjected to before. But one tube wasn't enough. The fuse needed 5: a transmitter tube to generate the radio signal, a receiver tube to detect the echo, 3 amplifier tubes to process the signal and trigger the firing circuit, 5 separate vacuum tubes, each one a potential failure point, all crammed into a space the size of a drinking glass, alongside the batteries, the antenna, the firing capacitor, and the detonator. Section T built their first working prototype in March 1941. They tested it not by firing it at aircraft, but by driving it past metal targets on a test track. The fuse detected the targets and triggered. It worked. On paper. The next test was harder. They loaded the prototype fuse into a 5-inch shell casing, drove to the Aberdeen Proving Ground in Maryland, and fired it from an actual naval gun. The shell exploded before it even left the barrel. The firing shock had caused a premature detonation. Back to the laboratory. Months of redesigns followed. The engineers added safety mechanisms to prevent the fuse from arming until the shell had been in flight for at least 400 yards. They reinforced the internal components. They tested different battery chemistries that could deliver high current without catching fire. They discovered that moisture was seeping into the fuse during storage and corroding the circuits, so they added waterproof seals. By summer 1941, Section T was conducting live-fire tests at the Naval Proving Ground in Dahlgren, Virginia. They fired shells at target drones, small radio-controlled aircraft that simulated enemy bombers. The early results were mixed. Some fuses worked perfectly, detecting the drones and detonating at the correct distance. Others failed completely. The failure rate hovered around 30%. Not good enough. Not even close. The work continued. More tests. More failures. More redesigns. The scientists weren't just fighting physics. They were fighting time. The war in Europe was expanding. Japan's aggression in the Pacific was escalating. Everyone at Section T knew that American involvement was coming, and when it did, the Navy would need this fuse desperately. December 7th, 1941. Pearl Harbor. Everything changed. The United States was at war. And Merle Touvet's proximity fuse was still not ready for combat. The attack on Pearl Harbor created a new urgency that bordered on panic. The Navy had just lost much of its Pacific battleship fleet in a single morning. Aircraft carriers would now bear the weight of the entire naval war against Japan, and those carriers were desperately vulnerable to air attack. The anti-aircraft defenses that had failed to stop the Japanese strike at Pearl Harbor needed improvement immediately, not in 6 months or a year. Immediately. Section T, now reorganized under the Johns Hopkins Applied Physics Laboratory, went into crisis mode. The team expanded to over 100 scientists and engineers working 3 shifts around the clock. Merle Touvet slept in his office. Some engineers didn't go home for days. The pressure was immense. Every week, without the proximity fuse, meant more American ships at risk, more sailors dead. The technical challenges remained formidable. The fuse had to be manufactured in quantities that the United States had never attempted for any electronic device. The Navy projected they would need millions of rounds, not thousands, millions, and every single fuse had to work. A failure rate of 30% was unacceptable. Even 10% was too high. When a shell costs $50 in 1943 and carries 5 vacuum tubes that each cost $3, and you're planning to manufacture 5 million of them, quality control becomes critical. Western Electric, the manufacturing arm of AT&T, took over mass production. They built entire factories dedicated solely to proximity fuse assembly. Workers, mostly women, sat at benches assembling components that they didn't fully understand but knew were classified at the highest level. Security was absolute. Anyone who worked on the fuse production line signed documents swearing them to secrecy. They couldn't tell their families what they built. They couldn't discuss their work outside the facility. Rumors spread that it was related to the atomic bomb project. The rumors were wrong, but the security level was the same. By August 1942, The first production-run VT fuses were coming off the assembly lines. Quality testing showed failure rates had dropped to 5%, still not perfect, but close enough for combat trials. The Navy's Bureau of Ordnance made a critical decision. The fuse would be introduced to combat under absolute secrecy. No fuse could be fired over land, where the enemy might recover a dud and reverse engineer the technology. No fuse could be fired where enemy forces might retrieve it from shallow water. The weapon could only be used in deep ocean naval engagements, where any unexploded shells would sink beyond recovery. And even then, gunners were not to be told what made these new fuses different. The shells arrived with stenciled markings reading, Mark 32, fuse, handle carefully, classified. That was all the information most gun crews received. The USS Helena received her first shipment of VT-fused ammunition in November 1942. 500 rounds loaded aboard at Espiritu Santo in the New Hebrides. Lieutenant Cochrane, the gunnery officer, attended a 30-minute briefing where he was told only that these shells would be more effective than standard-time fuses and that under no circumstances were they to be fired during shore bombardment missions. The specifics of how they worked remained classified above his clearance level. Which brings us back to January 5, 1943. The Helena, screening for cargo vessels supplying the Guadalcanal garrison, comes under attack by Japanese bombers. Cochrane's gun crews load the new ammunition. They don't know they're about to make history. They just know they're being attacked, and they need to shoot down the attackers before bombs start hitting their ship. The first Val begins its dive. Cochrane's crew tracks it, the gun captain calling out bearing and elevation, while the pointer and trainer work their controls to keep the long barrel aimed at the diving aircraft. They're not setting time fuses. These new shells don't require it. They just aim, load, and fire. The shell leaves the barrel at 2,800 feet per second. Inside the shell, the setback forces from launch compress a spring-loaded mechanism that, after 400 yards of flight, releases and allows the fuse to arm. Simultaneously, the centrifugal force from the shell's spin activates a small battery pack. Power flows to the 5 vacuum tubes. The transmitter tube begins broadcasting a radio signal at 175 MHz, pulsing 30 times per second. The antenna, a simple wire loop wrapped around the nose of the fuse, radiates the signal in a cone-shaped pattern ahead of the shell. The shell arcs upward. 3,000 feet altitude. 4,000. 5,000. The Japanese Val is still diving, now passing through 6,000 feet, its bomb load clearly visible, the pilot committed to his attack run and unable to maneuver aggressively without stalling. The shell and the aircraft are on a collision course, but they won't actually collide. The gunner's aim is slightly off. The shell will pass 50 feet to the left of the Val's flight path. 50 feet. In naval gunnery with time fumes, that's a complete miss. The shell would explode at whatever altitude its timer was set for, and the aircraft would fly through unscathed. But this shell doesn't have a timer. It has a radar transmitter that's been broadcasting for 3 seconds, sending out radio waves that bounce off anything metallic in their path. At a range of 300 yards, the return echo from the Val's aluminum airframe becomes strong enough for the fuse's receiver tube to detect. The signal processing circuit, a marvel of miniaturization built from 5 vacuum tubes and passive components, compares the transmitted and received signals. The return echo is getting stronger. That means the shell is approaching a metallic object. The circuit calculates. 100 yards. The echo strength increases further. 100 yards. 50 yards. The rate of change in the echo strength tells the fuse that whatever it's detecting is large, metallic, and very close. At 70 feet of separation, the firing circuit triggers. A capacitor that's been charging since the fuse armed suddenly discharges through a detonator. The detonator ignites the booster charge. The booster charge detonates the main explosive filler. The 5-inch shell contains 6.5 pounds of high explosive. When it detonates, that explosive converts into gas expanding at 23,000 feet per second, shattering the shell casing into approximately 1,500 fragments, travelling at velocities exceeding 4,000 feet per second. Those fragments spread in a roughly spherical pattern, creating a cloud of supersonic steel shrapnel 70 feet in diameter. The VAL is flying at 280 miles per second, 410 feet per second. The shell explodes 50 feet ahead and to the left of its flight path. The pilot doesn't see the burst. He's focused on his bombing run, watching the Helena's deck grow larger in his bomb sight. Then his aircraft flies directly into the expanding sphere of shrapnel. Dozens of fragments, each one carrying the kinetic energy of a rifle bullet, tear through the VAL's thin aluminum skin. The engine cowling shreds. The propeller disintegrates. 3 fragments punch through the cockpit canopy. The pilot dies instantly. The aircraft, no longer under control, continues forward for another 2 seconds on momentum alone before the damaged airframe breaks apart from aerodynamic stress. The bomb separates and tumbles toward the ocean, exploding harmlessly in the water 800 yards from any ship. From Lieutenant Cochrane's perspective on Helena's deck, he sees his shell explode near the target, and the target immediately disintegrates. He doesn't know why. The official explanation he's been given is that the new fuses are improved time fuses with better reliability. He assumes the gun captain somehow set the timer perfectly, and that perfect timing combined with good aim produced the kill. He doesn't realize the shell detected the target and made its own decision about when to explode. The second VAL dies the same way. Shell explodes nearby. Aircraft flies into the shrapnel cloud. Target destroyed. By the time the attack ends 4 minutes later, 2 Japanese aircraft are in the water, and the gun crews are jubilant. They've just achieved something that seemed almost impossible based on their previous combat experience. 2 targets engaged, 2 targets destroyed. A 100% kill rate. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Helena's action report, filed 2 days later, noted, anti-aircraft fire proved highly effective against attacking aircraft. New. Ammunition performed as advertised. That bland, bureaucratic language concealed what had actually happened. The proximity fuse had just made its combat debut, and it had worked exactly as designed. But the Navy wasn't ready to deploy it fleet-wide. Not yet. The security concerns remained paramount. If the Japanese recovered even one intact fuse, their engineers could potentially copy it. The technology wasn't so advanced that it couldn't be reverse-engineered. It was sophisticated, yes, but not impossible to duplicate. And if Japan developed their own proximity fuses, American aircraft would face the same lethal effectiveness that Japanese aircraft now faced. So through the first half of 1943, VT fuses remained restricted. Only selected cruisers and battleships received limited quantities. Gun captains were explicitly ordered not to fire them in shallow waters or within range of enemy-held islands. The weapon that could revolutionize naval anti-aircraft defense sat in magazines, used sparingly, its full potential untapped. The Japanese noticed something was wrong, but they couldn't identify what. Action reports from bomber crews that survived attacks on American task forces began noting that anti-aircraft fire seemed more accurate than it had been in 1942. Pilots reported shells exploding closer to their aircraft, bursts that seemed to track their evasive maneuvers. But without recovered evidence, Japanese intelligence couldn't determine if the Americans had developed new fuses or if their gun crews had simply become better trained. Lieutenant Commander Saburo Sakai, one of Japan's most experienced naval aviators, wrote in his journal after a June 1943 mission, American anti-aircraft fire has improved significantly. Multiple close bursts during our attack run, lost 3 aircraft from formation, cause uncertain, no direct hits observed. Sakai survived the war and later learned about proximity fuses. His reaction, if we had known about this technology, we would have fundamentally changed our attack tactics. By late 1943, production had ramped up sufficiently that the Navy began wider deployment. More ships received VT ammunition, the quantities increased, and the restrictions loosened slightly. The Solomon Islands campaign provided extensive combat testing. Battle after battle, task forces equipped with proximity-fused shells showed markedly better survival rates against air attack than those still relying entirely on time fuses. The statistical improvement was dramatic. In early 1943, before widespread VT fuse deployment, the Navy estimated it required an average of 2,500 rounds of 5-inch ammunition to destroy one enemy aircraft. By early 1944, ships firing proximity-fused shells were achieving kills with an average of 350 rounds. That was a 7-fold improvement in ammunition efficiency. 7 times fewer shells required per kill meant 7 times more aircraft destroyed with the same amount of ammunition. The human cost of that improvement is harder to quantify but no less real. Ships that might have been sunk stayed afloat. Sailors who would have died survived. Aircraft carriers that represented billions of dollars in construction costs and thousands of man-years of training continued launching strikes against Japanese positions instead of sinking to the bottom of the Pacific. The Battle of the Philippine Sea in June 1944 showcased the VT fuse's capabilities on a massive scale. The Japanese committed over 400 carrier aircraft to destroy the American task force. American fighters intercepted many of them, but dozens of Japanese bombers and torpedo planes broke through to attack the carriers and their escorts. The defending ships fired thousands of shells equipped with proximity fuses. The result was catastrophic for the Japanese. American pilots called it the Great Marianas Turkey Shoot. Of the 400-plus Japanese aircraft committed to the battle, only 130 returned to their carriers. The rest were shot down. How many of those losses came specifically from proximity-fused anti-aircraft fire versus fighter interception versus pilot error is impossible to determine precisely, but ships' action reports from the battle consistently noted high anti-aircraft kill rates. The USS Alabama claimed 6 aircraft destroyed with her 5-inch battery. The USS Indiana claimed 8. These were battleships whose primary purpose was shore bombardment and surface combat, not anti-aircraft defense, achieving kill numbers that would have been exceptional for dedicated anti-aircraft cruisers just 2 years earlier. Admiral Raymond Spruance, commanding the 5th Fleet during the battle, wrote in his after-action report, "Anti-aircraft effectiveness has reached levels that make conventional level bombing and torpedo attacks against task forces largely ineffective. Enemy aviation must develop new tactics or accept unsustainable losses." The Japanese did develop new tactics. They were called Kamikaze, special attack units, suicide attacks. If conventional bombing couldn't penetrate American defenses, perhaps pilots willing to die could crash their aircraft directly into ships, turning the airplane itself into a guided missile. The first organized kamikaze attacks began in October 1944 during the Battle of Leyte Gulf. The proximity fuse's effectiveness against kamikaze attacks became a matter of life and death for thousands of American sailors. A conventional bomber, if damaged by anti-aircraft fire, would typically break off its attack. The pilot's survival instinct would override his mission. But kamikaze pilots had no such instinct. They were committed to dying. Damaging their aircraft wasn't enough. You had to destroy it completely, kill the pilot, or cause catastrophic structural failure that made controlled flight impossible. The 5-inch proximity-fused shell could do all three. The shrapnel cloud it created was dense enough to shred airframes, kill pilots through penetration of the cockpit, and sever control cables. A kamikaze hit by a proximity burst might continue flying on momentum for a few seconds, but without a pilot or control surfaces, it would tumble or veer off course, missing its target. The destroyer, USS Lafay, experienced this reality on April 16, 1945, during the Okinawa campaign. The ship came under attack by 22 kamikaze aircraft over an 80-minute period. Her 5-inch guns, firing proximity-fused shells as fast as the crews could load them, destroyed 8 attackers outright. Her 40mm and 20mm guns, which couldn't use proximity fuses due to their smaller caliber, damaged several more. 6 kamikazes hit the ship. The Lafay survived, badly damaged but still afloat, and limped back to port. Without proximity fuses, analysis suggested the ship would likely have taken twice as many hits and almost certainly would have sunk. Multiply that story across hundreds of ships and thousands of attacks. The proximity fuse didn't make ships invulnerable. Kamikazes still got through. Ships still sank. Sailors still died. but the casualties were significantly lower than they would have been without the technology. Post-war analysis by the Navy's Bureau of Ordnance estimated that proximity fuses reduced kamikaze effectiveness by approximately 40 to 50% compared to what time fuses would have achieved. That percentage represents thousands of American lives. It also represents a strategic advantage. Every kamikaze that missed or was shot down was an aircraft and a pilot that Japan had expended for no result. Japan's industrial capacity couldn't replace aircraft losses at anything approaching American production rates. Every wasted attack brought Japan closer to having no air capability at all. By spring 1945, the proximity fuse was no longer secret. The Allies had begun using them in Europe during the Battle of the Bulge in December 1944, firing them from ground-based anti-aircraft guns to protect against German Von flying bombs. Once used over land, the security restrictions that had limited Pacific deployment evaporated. The weapon was now fully deployed. German engineers did eventually recover intact fuses and attempted to reverse engineer them. But by that point in the war, Germany's industrial capacity was so degraded that mass production was impossible. Japan never successfully recovered an intact fuse for analysis. Their intelligence services knew the Americans possessed some kind of improved anti-aircraft technology, but the specifics remained unclear until after the surrender. The final toll is impossible to calculate precisely, but historians have attempted estimates. Between January 1943 and August 1945, the U.S. Navy fired approximately 2 million proximity-fused 5-inch shells in combat. Those shells contributed to the destruction of thousands of enemy aircraft. They protected carriers, battleships, cruisers, destroyers, and transport vessels carrying hundreds of thousands of American servicemen. The technology that Merle Tuve and his team developed in a wooden building in Maryland, working 80-hour weeks under impossible pressure, fundamentally altered the Pacific War's trajectory. But the story doesn't end in August 1945. The proximity fuse's legacy extended far beyond World War II. The basic concept, using radio or radar to detect proximity and trigger detonation, became foundational to every air defense system developed afterward. Modern surface-to-air missiles use sophisticated radar fusing. Artillery shells fired by systems like the M109 Paladin can be equipped with proximity fuses for airburst effects. The Phalanx CIWS, the close-in weapon system that defends modern warships, fires tungsten penetrator rounds using a radar system that's a direct descendant of Tuve's work. The principle expanded beyond anti-aircraft applications. Modern anti-tank munitions use proximity sensors to detonate above armored vehicles, directing shaped charge explosions downward through thinner top armor. Cluster munitions use proximity fuses to disperse sub-munitions at optimal altitude. Even non-military applications emerged. Some avalanche control systems use proximity-fused charges to trigger controlled slides before dangerous snow buildup occurs. The VT fuse also represented something broader about the relationship between science and warfare. World War II was the first major conflict where scientists in laboratories directly influenced battlefield outcomes at strategic scales. The Manhattan Project gets most of the attention, and deservedly so, but the proximity fuse arguably saved more American lives than the atomic bomb ended Japanese ones. The bomb ended the war. The fuse helped win it. After the war, he returned to civilian research, eventually becoming director of the Carnegie Institution's Department of Terrestrial Magnetism. He rarely discussed the proximity fuse in public, and when pressed, would credit his team rather than himself. In a 1963 interview, one of the few times he spoke at length about the project, he said, "We were just trying to solve a problem. The problem was that American sailors were dying because we couldn't shoot down enough enemy aircraft. We solved it. That's all." That understated assessment concealed the magnitude of what had been achieved. Section T had taken a theoretical concept that most engineers considered impossible and turned it into a practical weapon system in less than 3 years. They'd miniaturized radar technology that normally filled rooms into a package the size of a soda bottle. They'd made that package survive, forces that would destroy most mechanical devices. They'd manufactured it in quantities of millions with failure rates below 5%, and they'd done all of it while maintaining absolute secrecy about how it worked. The gun crews who fired those shells mostly never knew the technical details. Seaman Thomas Reardon, who witnessed Helena's first combat use in January 1943, survived the war and returned to Iowa, where he worked as a mechanic. In a 1987 oral history interview, he recalled that day off Guadalcanal. "We knew something was different about the new ammunition. The shells seemed to explode closer to the targets. We figured the Navy had improved the fuses somehow, made them more accurate. We didn't know how. We just knew it worked." Lieutenant Red Cochran, Helena's gunnery officer, had a higher level clearance and received a more detailed briefing about proximity fuses in late 1944. His reaction, recorded in a letter home: "You wouldn't believe what these things do. They're like something from a Buck Rogers comic. Make me wonder what other secret weapons we've got that I don't know about." The Japanese perspective is harder to document comprehensively. Most of the pilots who could have provided detailed accounts about facing proximity-fused anti-aircraft fire didn't survive the war. The ones who did survive often had fragmented memories of specific engagements, making it difficult to separate which attacks they faced, conventional time-fused shells versus proximity fuses. But the aggregate data is clear. Japanese naval aviation never recovered from the losses sustained during 1944 and 45. The Marianas Turkey Shoot, the Philippines campaign, the battles around Okinawa all showed the same pattern. Japanese aircraft attacked. American anti-aircraft fire destroyed them in numbers that Japanese training pipelines couldn't replace. Some historians argue the proximity fuse should be ranked among the top technological innovations of World War II, alongside radar, the atomic bomb, and the aircraft carrier. Others contend it was simply one of many incremental improvements that collectively produced Allied victory. The truth probably lies between those positions. The fuse alone didn't win the war, but it was a critical component of a larger system of technological and industrial superiority that overwhelmed the Axis powers. What's undeniable is the human impact. Every kamikaze shot down before impact was a ship that didn't sink, a crew that went home instead of dying. Every conventional bomber destroyed meant fewer bombs hitting their targets, fewer casualties among invasion forces, less damage to fleet logistics. The mathematics of warfare are brutal but simple. Increase enemy losses while decreasing friendly losses, and you win. The proximity fuse did exactly that. The device also represented a philosophical shift in how military technology developed. Before World War II, weapons innovation typically came from within the military establishment itself. Arsenals and proving grounds designed new artillery. Naval engineers designed new ships. The civilian scientific community remained largely separate. The Proximity Fuse project, alongside radar development and the Manhattan Project, established a new model where civilian scientists worked directly on military applications, bringing expertise the military didn't possess internally. This model continued through the Cold War with organizations like DARPA, Defense Advanced Research Projects Agency, which funded cutting-edge research at universities and private laboratories. The Internet itself emerged from DARPA funding. GPS began as a military navigation system. Countless technologies that civilians now use daily trace their origins to defense research programs following the model that Vannevar Bush and Merle Tuve pioneered with Section T. The proximity fuse's operational life gradually ended as technology advanced. By the 1960s, surface-to-air missiles had largely replaced gun-based anti-aircraft systems on major warships. Missiles offered longer range, higher accuracy, and more sophisticated guidance than even the best gun systems. 5-inch guns remained on ships for shore bombardment and surface combat, but their anti-aircraft role diminished. The last major combat use of proximity-fused 5-inch shells was probably during Vietnam, where destroyers and cruisers provided naval gunfire support and occasionally engaged North Vietnamese aircraft. Modern naval vessels still carry guns, but they're secondary weapons. The primary defense against air attack comes from missiles, the Aegis system, electronic warfare, and decoys. If an enemy aircraft gets close enough for guns to engage, something has already gone very wrong. The age of massive anti-aircraft barrages, ships hurling thousands of shells skyward in desperate attempts to stop incoming attacks, ended decades ago. But the lessons remain relevant. The proximity fuse demonstrated that the difference between success and failure in combat often comes down to how effectively you can apply technology to solve specific tactical problems. The problem wasn't that American sailors weren't brave enough or skilled enough. The problem was that the tools they'd been given, time-fused shells requiring perfect calculations under stress, weren't adequate for the mission. Give them better tools, tools that solved the hard parts of the problem automatically, and their effectiveness multiplied. That principle applies far beyond anti-aircraft fire. Military technology development is ultimately about reducing the burden on individual operators, taking complex tasks and making them simpler, faster, more reliable. A soldier using an infrared scope doesn't need to be able to see in the dark naturally. The technology does it for him. A pilot using GPS doesn't need to be an expert navigator. The system handles the calculations. A gunner using a proximity fuse doesn't need to perfectly calculate time and distance. The fuse makes its own decision. Each of these technologies shifts cognitive load from the human to the machine, freeing the operator to focus on higher-level decisions. The sailor firing the proximity-fused shell still needs to aim properly and lead the target correctly. But he doesn't need to simultaneously predict exactly when the shell will reach the target's altitude and set a timer accordingly. That's one less thing to think about during the chaos of combat, and that reduction in mental workload translates directly to better performance. The engineers who designed the VT fuse understood this intuitively. They weren't trying to replace human gunners with robots. They were trying to augment human capability to handle the one part of the task that humans couldn't reliably do under stress. Everything else, the aiming, the tracking, the decision about when to fire, remained human. Only the final decision about when to detonate moved from human judgment to electronic sensing. This human-machine partnership became the template for modern military technology. Fighter jets use fly-by-wire controls that wouldn't allow the pilot to make inputs that would stall or overstress the aircraft. Tank fire control systems measure wind speed, range, ammunition type, and ballistic characteristics, providing the gunner with an aim point that accounts for all variables. None of these systems replace the operator. They enhance them. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.